Hello everyone, I am Shreya Maka, and on behalf of my co authors, I'd like to present our paper Seeing Double Image to Image Diffusion for Multi Transformation Visual Anagrams. The first question we encounter upon hearing this title is what is a visual anagram? Here is an example. This is an image that looks like a fruit bowl, but when you rotate it, it becomes a monkey. This is called a visual anagram, which is one image but two interpretations. Just like word anagrams rearrange letters to form new words, visual anagrams reinterpret the same pixels to reveal two different images. In the next few minutes, I'll walk you through the motivation, methodology, implementation, and results of our work. The problem we address is synthesizing an optical illusion using diffusion models. We generate a single image that satisfies two different prompts without compromising either meaning. Our work builds on a 2024 paper by Geng et al., which introduced the initial method to generate visual anagrams. This initial work focused on single transformations and textual inputs to generate a visual anagram. Rather than redesigning the underlying system, we investigate how it can be extended to multiple composite transformations, which also apply to images as inputs. Now, my co author Aditi will explain the architecture and novelty of our work.
I'm Aditi. I'm going to talk about our key contribution. Our first key contribution is fully image condition multi-view diffusion framework. Unlike the original visual anagram framework, which operates purely in text-to-image setting, our approach uses reference image as an additional conditioning signal. This allows us to preserve the overall structure of the image while generating multiple semantic interpretation under different transformation. Our second key contribution is combined view operator. Combined view operator enables multiple compatible transformations such as rotation and color permutation, rotation and negation, which will be further explained by my co-author Nishant. The combined view operator significantly expands the transformation space and improves the generation flexibility. We introduce new transformations like patch permutation, color permutations, etc. This helps to produce much clearer and different visual anagrams. I'm going to talk about the architecture of our paper. We are going to pass two inputs to our visual anagram input image, which is the reference image, and the second is the prompt. The text prompt is passed through the profanity check for the ensuring safe prompts. The first stage is a low resolution image to image generation, which is based on the deep Floyd. At this stage, the model generates a coarse 64 into 64 visual anagram. We apply multi-view denoising where different transformed views of the same image are processed simultaneously. The noise prediction from all the views are aggregated into a single update direction, ensuring consistency across all the views. In stage 2, takes the input of stage 1 64 into 64 image to produce the upscaled 256 into 256 resolution using deep Floyd super resolution model. Multi-view consistency is maintained during this refinement process, allowing edges, texture, and fine details to become sharper while preserving the intended visual illusion. Finally, in stage 3, takes 256 into 256 image as an input to produce higher resolution output of 1024 into 1024 pixels. The stage improves the visual quality and photorealism while retaining the semantic consistency across all the transformed views. The final output from the stage 3 is passed through the animation function to get the animations, and the metrics are collected using the functions which is further explained in our paper and in her GitHub code. We'll go through the example how actual output looks. This is how the stage 1 output size would be. The output of stage 2, the output of stage 3. The final stage would after stage 3 would be an animated video, which would be often in this format where we can see both the visuals. The next about the pipeline will be further explained by Markham.
I will be briefly explaining the diffusion pipeline, which is utilizing Deep Floyd. The first step is pre-processing the input text prompts. These textual inputs are encoded using Deep Floyd's inbuilt T5 encoder. Next, we pre-process the input image via the PIL module. These inputs proceed to the 3 stages which synthesize the visual anagram. Stage 1 consists of a denoising loop, where we apply the transformation views and apply the Deep Floyd diffusion model to repeatedly denoise the image. This loop contains the apply views function, which is followed by a unit forward pass, and then an inverse view reconstruction, then a CFG combiner, as well as a scheduler step to complete the loop. This denoising loop can be seen utilized in the stage 2 as well. The 64 by 64 output of stage 1 is then sent to stage 2, which performs the dual task of upscaling and denoising the generated latent. The output of stage 2 is an upscaled image of dimension 256 by 256, which is a larger and clearer image. This is then passed to the final stage, where it is upscaled to 1024 by 1024 dimension. This image is the final output of the diffusion pipeline, which is used to generate the animation and is evaluated using the generated metrics. Now my co-author Nishant will be explaining further.
Hey everyone, I'll be explaining the different transformations. So these are the transformations which were there in the original paper. And now I'll be explaining the new transformations that we have created on our own. So starting with the first is color rotations and color permutations. Instead of changing the geometry of the image, these transformations operate in the RGB color space. By rotating or rearranging color channels, we can create different visual interpretations while preserving the underlying image structure. This allows us to generate color-based illusions that were not possible with traditional geometric transformations. So these are the examples of color-based rotations. Now let's look at more examples. Next, we introduce triangle-based transformations. The image is divided into triangle regions, and these triangles can either be flipped or permuted. This creates local geometric variations while maintaining the overall composition of the image. As a result, different views can emerge from the same generated image. Now let's look at examples for triangle-based transformations. These are examples for patch flipping. These are more examples for triangle-based permutations. Okay, now let's go to the third transformation. The third transformation is patch flipping. Here, the image is divided into n cross n grid of patches, such as 8 cross 8 or 16 cross 16. Each patch can be flipped horizontally or vertically. These local changes create new visual patterns while preserving the global structure required for multi-view generations. So these are the examples for vertical patch flipping. And these are the examples for horizontal patch flipping. Now, why is combination needed? While each transformation individually increases the diversity of outputs, using only one transformation at a time limits the number of possible visual anagrams. To overcome this, we introduce a combined view operator. Combined view allows multiple compatible transformations to be applied simultaneously within a single diffusion process. For example, a color transformation can be combined with patch flip transformation. This greatly expands the transformation space and enables more complex, diverse, and controllable visual anagrams while maintaining image quality and consistency across all views. So these are a few examples for image to image combined transformations. Now, my co-author Shreya will be discussing the results.
Hello, everyone. Before discussing the results, I'll briefly explain the evaluation metrics. Clip A and Clip B measure semantic alignment between each generated view and its intended prompt. Higher values indicate that the generated image correctly represents the target concept after transformation. The concealment score measures how well the different concepts remain hidden from each other. A higher score means the two interpretations are better separated, which is important for a convincing visual anagram. LPIPS measures perceptual difference between the transformed views, and higher values are desirable because the two views should appear meaningfully different when the transformation is applied. Finally, SSIM measures structural similarity. Since our transformed views often represent completely different concepts, moderate SSIM values are expected rather than extremely high ones. Now, looking at the combined transformation results, our method applies multiple compatible transformations together in a single generation process, whereas the baseline applies each transformation independently. Visually, we can clearly see that our outputs produce two strong and recognizable concepts simultaneously. For example, in the skull Einstein and the bird pig examples, both transformed views are convincing and maintain good visual quality. In contrast, the baseline often shows an imbalance where one transformation produces a strong result while the other appears weaker or less recognizable. The metrics support these visual observations. Our method maintains strong clip alignment while achieving high LPIPS and concealment values, indicating that the views are both semantically correct and perceptually distinct. Moving to the combined plus image to image results. We additionally introduce image conditioning using a reference image, which acts as a structural anchor during generation. Here, the improvement is even more noticeable. Examples such as Waves Dragon and Cherry Blossom's Parrot preserve the style and structure of the reference image while still producing two clear interpretations. The outputs are more coherent, visually appealing, and balanced across both views. An important observation is that baseline methods often exhibit unbalanced transformation behavior, leading to asymmetric clip scores and inconsistent quality across views. We also observe that SSIM may decrease for geometric transformations such as rotations, since it is sensitive to spatial misalignment. However, this does not necessarily indicate poorer anagram quality. The relatively strong LPIPS scores show that perceptual consistency is preserved even when SSIM decreases. Furthermore, image to image conditioning improves consistency across the metrics, increases concealment, and reduces cross view interference, resulting in more balanced outputs. In conclusion, our work shows that image conditioned diffusion and composable transformations can successfully overcome the limitations of existing visual anagram methods. The resulting images are more balanced, consistent, and visually convincing across multiple views, demonstrating a significant step towards more controllable and expressive multi-view generation systems. Please visit our GitHub page if you found our project interesting and you wanted more details. Thank you.